In section 1.6, we're going to discuss solving linear inequalities. Basically, the idea is the same as solving a linear equation. You sort of do the same thing to both sides of the inequality, just like you would do the same thing to both sides of an equation. The one thing that you have to watch out for here is if you multiply or divide by a negative number, you have to flip the inequality. Let's take a look at an example. In this case, we want to both solve and graph the following inequalities. In part 1, 5x minus 7 is less than 3 minus 2x. And in part 2, 13 minus 5x is greater than or equal to 10x minus 1. Let's head to the whiteboard app where we can solve this example. In part 1 of this example, we're looking to solve the inequality 5x minus 7 is strictly less than 3 minus 2x. We're going to proceed like we would usually solve this as if it were an equation. First step, we're going to add 7 to both sides. Now, I'm going to do 2 steps in one here, so I'm simultaneously going to add 2x to both sides as well. What that's going to leave on the left-hand side is 7x, and on the right-hand side of the inequality, we're going to end up with a plus 10. Now, at this point, we divide both sides by 7, and we end up with the inequality x is strictly less than 10 over 7. So at this point, we want to graph this in the solution set of this inequality. First things first, I draw my number line. Now there's only one number of interest that I really care about here, and that's 10 over 7. So I put that on my number line. Next up, I put a parentheses here at 10 over 7 facing to the left for a reason that we'll see in just a second. In this case, x is strictly less than 10 over 7. Since x is less than 10 over 7, the solution set is everything to the left of 10 sevenths. So we shade into the left of this parentheses. Now, this parentheses is a parentheses because of the strict inequality that shows up in the solution x is less than 10 over 7. What I mean by strict inequality is there's no equality there. So it's not less than or equal or greater than or equal, it's less than or greater than. That's what it means to say strict inequality. On the other hand, if we had a less than or equal or greater than or equal, that's called a non-strict inequality, in which case we would put a bracket, a square bracket on our number line. Once we have our solution set drawn, we can write down the solution set in interval notation as the interval from minus infinity to 10 over 7. So you'll notice here that the parentheses on the 10 over 7 is the same parentheses that showed up on the number line. The minus infinity here is just a reflection of the fact that this interval that I've shaded in blue in this particular case continues on all the way back. There's no lower bound to that at all. So don't think of minus infinity as a number. It's just a concept, and basically what it means is the interval doesn't stop going to the left. For that reason, infinity and minus infinity always get parentheses in interval notation. This interval is our solution set. The graph that we drew above is the graph of that solution set. So at this point, go ahead and stop the video, pause the video, and try to work your way through the second half, which is 13 minus 5x is greater than or equal 10x minus 1. Come on back when you're ready and you can see my solution. So the first step that we're going to take here is to subtract 13 from both sides. That'll move the constants over to the right-hand side. And to subtract 10x from both sides. And what that'll leave is minus 15x is greater than or equal minus 14. At this point, we want to divide both sides by minus 15. What that's going to leave is x is less than or equal 14 over 15. You'll notice here that the inequality flipped. And this is an important point. Anytime you multiply or divide by a negative number in an inequality, you have to flip it around. We can now graph our solution set. So once again, we draw our number line, putting the only thing of interest on this number line, which is 14 over 15. In this case, I get a bracket at 14 over 15 because it's less than or equal. We shade to the left of that bracket because x is less than or equal 14 over 15. What this gives us as a solution set in interval notation is the interval from minus infinity to 14 over 15 with a bracket on the end at 14 over 15. You'll notice here that the brackets match up as well. This is our solution to this particular exercise. Now, you may have done things slightly different. For instance, you may have added 1 and added 5x to both sides. Your work will look a little bit different in between, but you should come up with the same answer as me. Next up, we're going to talk about compound inequalities. So when two inequalities are joined by the word and or the word or, a compound inequality is formed. These guys get some confusing and special names. So a conjunction is when two inequalities are joined by the word and. So this is called a conjunction. So for example, -3 is less than x and x is less than or equal to 2. So there's a common way to abbreviate this particular conjunction. And that's that -3 is strictly less than x, which is in turn less than or equal to 2. Notice that there's two inequalities in the same statement here. Disjunctions, on the other hand, contain the word or. So for example, -3 is less than x or x is less than or equal to 2. Unfortunately, there's no easy way, actually there's no way at all, to abbreviate disjunctions. In particular, you cannot write these inequalities in a whole string. Essentially, that's because of the transitive property of inequalities. And what that essentially says is if x is greater than y and y is greater than z, then x is greater than z. If you're taller than your middle brother and your middle brother is taller than your baby brother, then you're taller than your baby brother, in other words. And inequalities work in the same way. And that essentially forbids us from being able to abbreviate disjunctions in the same way that we can abbreviate conjunctions. It's unfortunate, but it's a fact of life. So in the next example, we're going to solve the following compound inequalities. In the first part of this example, we have a conjunction. -3 is strictly less than quantity 2x plus 5, which is in turn less than or equal to 7. And in the second part of this example, 2x minus 5 is less than or equal to 7, or 2x minus 5 is greater than 1. So we'll head over to the whiteboard app where we'll see a solution to these two compound inequalities. In the first part of this example, we're asked to solve the conjunction -3 is less than 2x plus 5, which is in turn less than or equal to 7. So essentially the way to solve a conjunction is to just sort of pretend that you have 3 sides of an equation to work with instead of 2. But everything else goes through pretty much the same. We're going to try to isolate x here, and the first step along that path is to subtract 5, but instead of being from both sides of an inequality, now it's from, so to speak, all 3 sides of the inequality. So on the very left-hand side, we get -8. In the middle, we get 2x. And on the right-hand side, we get 2. That's 7 minus 5. Next up, we want to isolate the x by dividing all 3 sides by 2. And what we end up with is -4 is strictly less than x, which is in turn less than or equal to 1. Now, this is an and inequality. So when we graph this thing, we're going to end up getting what's called an intersection. And you should remember this from intermediate algebra or wherever you took the prerequisite for this class, but we'll get a small refresher here. So as usual, we want to graph this thing, so I make my number line, and there's 2 numbers of interest here. The first is -4, and the second is 1. Now at -4, we get a parentheses and we shade to the right. The parentheses is a result of the fact that we have strict inequality in the inequality -4 is less than x here. On the other hand, the 1 gets a bracket. That bracket coming from the fact that we have x is less than or equal 1. And this time we shade to the left. You'll notice I did my shading in 2 different colors here. The first inequality is shaded in blue, the second inequality is shaded in purple. Now for an and inequality, that is a conjunction, we want the set of all x values, which are both greater than 4 and less than or equal to 1. So where that falls in this picture is the region that's between these two, that is, that's shaded both purple and blue. Mathematically speaking, that's called the intersection of the interval from -4 to infinity and -infinity to 1, closed at the 1 side. We write that as the interval from -4 to infinity intersect this little symbol here, that upside down U, is called sometimes a cap, but it's usually read intersect. So -4 to infinity intersect -infinity to 1, bracket at the 1 side.
So what we're looking for here is x values that are shaded both purple and blue. And in the end, that's the interval from -4 to 1 with a parentheses at -4 and a bracket at 1. For part 2 of this example, we're asked to solve the following disjunction, the OR inequality. 2x minus 5 is less than or equal to 7, or 2x minus 5 is greater than 1. So in this case, we can't work with an abbreviated form. Unfortunately, you can't do that with disjunctions. So what we're going to do is solve each one of these inequalities separately. In both cases, we're trying to isolate the x. So in that first inequality, we're going to add 5 to both sides. And we're going to do the same in the second inequality. And what we end up with in the first inequality is 2x is less than or equal to 12. And in the second inequality, 2x is greater than 6. We then divide both sides of each inequality by 2 to isolate the x. What this gives is x is less than or equal to 6, or x is greater than 3. Now, once again, we want to graph both of these inequalities separately. So we first graph our number line. There's two numbers of interest here. One is 6 and the other is 3. The first inequality is x is less than or equal 6. So we get a bracket at 6 shading to the left. We get a parentheses at 3 shading to the right because of the strict inequality x greater than 3. Now, the OR inequality here, we want to find all numbers x which are shaded either purple or blue. And if we look at the picture here, the first region is shaded purple only, the middle region is shaded both purple and blue, and the last region is just shaded blue. Now, if you're shaded both colors, that counts as being included in the OR statement. This is sometimes called an inclusive OR as opposed to an exclusive OR. I don't want to get too much into the details there, but suffice it to say, if you're both colors, you're at least one. So in the end, everything on this number line is shaded at least one color. And for that reason, our solution set goes all the way from -infinity to infinity. In the end, this solution set is the union of the interval from -infinity to the 6 with a bracket on the 6, together with the interval from 3 to infinity with a parentheses on the 3. We write that as the interval from -infinity to 6, bracket, and then a u, but it never gets the hook on the end here. So notice that this symbol here does not have a hook on it. We never put the hook there. Union is what that symbol is read as, the interval from 3 to infinity, parentheses at both sides.
Next up, we're going to take a look at example 4 in the book. So this is on page 141. In this example, for her house painting job, Erica can be paid in one of two ways. On plan A, she makes $250 flat fee plus $10 per hour. And on plan B, she makes $20 per hour. Suppose that the job takes n hours. For what values of n is plan B better for Erica? So we'll head on over to the whiteboard app and we'll solve this example.
So notice in this exercise, in the statement of the problem, they essentially do the define step for us. Namely, they tell us to let n be the time it takes Erica to do the job. Just for the sake of completeness here, even though they defined the variable for us, notice that a time is a number in whatever units it happens to be measured in this particular case, hours. Second of all, doing the job is the sort of specificity part of the define step in this particular problem. So next up, we need to write down an equation. And in this case, it's not exactly an equation. What we're going to end up with is an inequality. And more specifically, that inequality is 250 plus 10 times n is strictly less than 20n. So on the left-hand side of the equation, this is the total pay that Erica will receive if she charges on plan A. And on the right-hand side, 20n is the total pay that Erica will receive if she charges on plan B. What it means for plan B to be strictly better for Erica than plan A is if the right-hand side is strictly greater than the left-hand side. Notice this is exactly the opposite of what would be better for the customer, but we're not interested in that here. Next up, we got to solve this inequality, which in this case is pretty straightforward. So we start off with 250 plus 10n is less than 20n. and we subtract 10n from both sides. On the left-hand side, that leaves 250, and on the right-hand side, that leaves 10n. We then divide both sides by 10, and what we end up with is 25 is strictly less than n. We take this inequality and we turn it into a statement that solves the problem. In this case, Plan B is better for Erica, provided the job takes strictly more than 24 hours. 25 hours.
So that concludes section 1.6 on solving linear inequalities.